So in this video, I'm going to talk about center of mass, and this is going to be the first part of a four-part video series on center of mass. And in this video, I'd specifically like to talk about the definition of the center of mass and do a couple of very basic explanations of it. So first and foremost, the definition of center of mass is a unique point. There's only one center of mass for a region or for an object where the weighted relative position of the distributed mass sums to zero. So that means that if I take the stuff on the left side and make it negative, the stuff on the right side and make it positive, then they should eventually equal out to zero if I combine them all. And what's important is that we're talking about the relative position and a mass. So we're talking about two things. We're talking about a distance, usually from the origin if we're talking about just one dimension. If we're talking about more than one dimension, we'll talk about the axes and its mass, or sometimes referred to as its force, just depending on what area of physics you're working on. This is also called the balance point. And the reason we call it the balance point is because if we have a region or if we have a fulcrum, then it should achieve balance if it's set upon that one center of mass, that one particular point, and just kind of left to hang. It should balance completely at that point, not tip over one direction or another. And I will also mention to you that this is very similar in operation in its work to the weighted average, because what we're going to do is we're going to take essentially its mass as its value, and we're going to multiply it by its relative position, its distance. And what that does is it should give us essentially a weighted average of the masses and the distances. So while I'm talking about this, I'm going to go ahead and mention one of the kind of physics applications of it, which is the law of levers. And so if we have a lever, which is any rigid object, could be like a seesaw or a bar, it's usually represented by some line segment, and it's going to pivot on a fulcrum. So here's my lever, and I'll draw a fulcrum right here, something for it to pivot on. And it's going to achieve balance, because remember, if it's a lever or a seesaw, it could go one direction or another. And the thing is, it's going to achieve balance when the cross product of the forces and distances are equal. So, for example, if I have something really big or really heavy over here, it's going to exert more force on it, kind of in that, I'll call it a down direction. And so what I'm going to do is I'm going to say that its distance, since this is heavy, should be pretty close to the fulcrum if I choose something that's much lighter, which is going to kind of give me a different direction of force. It's going to go up instead of down. What is going to happen is this should be much farther from the fulcrum in order for it to balance. So again, we want our masses or our forces and our distances to essentially balance each other out. We want them to be like the sides of an equation. So if I have the force or the mass of the left side times how far it is on the left side, so notice we're just all working on the left side here, it should be the same as the force times the distance, or the mass times the distance of the right side. I will mention to you that when this occurs, when the lever is at balance on the fulcrum, the position of the fulcrum is actually the center of mass. So, for example, in this situation where I have this perfect balance between these two weights, right there where the fulcrum meets the lever, that is going to be where the center of mass is. I'm going to go a little bit further and talk about how to find the center of mass for a one-dimensional system. Now, again, this is just using x values or y values. It's just one dimension of distance. And so when I talk about the moment of mass, that is usually done by taking the mass of each individual object, so I'll write mi, times its distance, or we could call it its x value, so xi. And so that's the moment of mass. So these are individuals. Now, I'm going to use another, it says moment, but I'm going to be very specific. This is called the moment of the system. This is the combined, this is the collection of all individuals. And again, we typically take it about the origin. We have some place to measure it from. And so what we're going to do for this is I'm going to call it M0 for M of the origin, M of the system. And it's just going to be the summation of all of the individual moments. So I'm going to start at the first one, and I'm going to multiply all of the masses times the distances and just add them all up. So again, this is why it's very, very similar to a weighted average, because that's actually the definition of a weighted average right there. Now the center of mass, which we typically write as x bar for average, or average x value, is going to be the moment of the system, a moment of zero, divided by the total mass. So let me write that down. Moment of the system divided by the total mass. So I could also write that using that sigma notation, that summation. So it's going to be all of my point masses, all of my mass times the distance or its location divided by just the masses. Now, these will not cancel out and just give you those x values. It's not going to average the x values together. It's going to include the weighted average. So now that I've kind of gone over all the formulas that are important and all this information about what the center of mass is, let's actually do a problem involving the center of mass. So I've got point masses, mi, that are located on the x-axis, and I even drew myself a little x-axis down here, where M1 is 40 at x1 equals 20. So notice there's my mass of 40 at an x value of 20. And I have another point mass, which is 30 at 5. So notice there's my mass of 30 at 5. And I tried to draw this at least a little bit to scale, because notice this circle is a little bit bigger than the other one because it's supposed to weigh a little more. It's a little more massive. And it says, at what x coordinate is the center of mass located? Well, the first thing I'm going to do, I'm going to find the individual moments of mass. So I'm going to do this first part. So 40 times 20, my mass times my distance. And that's going to give me 800. So there's my first moment of mass. The other moment of mass is going to be the mass at 30 times 5, its location, which is going to give me 150. So these two are my moments of mass. These are my individuals. If I want to find the moments of the system, I just have to add them together, which is 950. And the last thing that I need to do is I need to take that 950, that moment of the system, and I need to divide it by the total mass, which is 30 plus 40. Now 30 plus 40 gives me 70, so 950 over 70. When I divide, I know that doesn't simplify. Let me go ahead and make sure I got it in my calculator. It should be approximately 13.57 and some change. So that means my center of mass, x bar, is at approximately 13.57. Now, I think it's kind of important to note that, as you notice, it's not exactly halfway between 5 and 20. Halfway between 5 and 20 should be somewhere around 12.5, but 12.5 is right about there. But our actual center of mass is right about here, which is 13.57. And the reason that is because this bigger mass is kind of pulling the center of mass towards it. The heavier something is, the more massive something is, the shorter the distance it needs to be. All right, so hopefully that helps you kind of better understand the idea of center of mass. Please feel free to let me know if you have any questions. Have a great day.